There's a pleasure to produce one of the new INSA fellows. Marcia was part of an incredibly high competition, very high level of competition that applied for this. And she's an important exponent of Brazilian mathematics. We are very proud to have her here. And Marcia Federson from the Universidade de Sao Paulo is going to be speaking here about non-absolute integration. Marcia?
Thank you very much for the nice introduction. It's again a pleasure to be here with you. When Ludwig talked to me on the phone about the procedures and everything, he explained, Marcia, this is a very general audience, so you should address your issues to that audience, which is not specified for differential reasons, as I used to. So my goal here is to give you an idea, and this is, I want you to understand the partitioning and the thinking of domains of integration, the limiting process of integrations, and of theories of integrations, and the connection of these things in blue with quantum mechanics. If this is okay in your mind, then I'm done. I'm happy. Then I'm going to mention some things. So the best known theory of non-absolute integration is due to these two guys. It's very nice that we have two pictures of them together on the internet. This is one of them. So we have the British Rob Henstock and the Czech Jaroslav Kurzweil. Okay, Jaroslav lived a long life. I was able to meet both of them. They were very nice. And they define a very general and powerful integral. Of course, I'm selling my product here, so this is, I'm going to say that it's powerful. In terms of human sums, and this is very simple. And it was called generalized human integral. And when I first realized that I was having problems that I mentioned to you, writing problems to my students, saying that I was doing something like Kurzweil-Henstock integration, then I changed it to generalized human integration, because we were not going to argue with human. So, okay, then another name for this integral is generalized Perron integral. So what we have for finite dimensional spaces is this picture here. We have the Riemann integral, and then the Lebesgue integral, and then the Kurzweil-Henstock integral. Improper Riemann integral, we know there are some functions which are not Lebesgue integrable, but if you pass the limit, you extend a little bit the Riemann integral. And when you do this by improper integration, this is called Cauchy extension. So we have Lebesgue with his PhD thesis in 1902, clearly generalizing the full Riemann integral and adding to the set of integral functions, those functions with many distributions. But we know that a function is like integrable if and only if it's integrable in the absolute value of it. And of course, for other spaces, we have the ordinary integral. Okay, so Danjois, a French mathematician, tried to think of non-convergent functions, or the sequence of functions, so that they would not be integrable in an absolute way. Also, people wanted to have a fundamental theorem of calculus without adding any assumptions on the integral, so that you could have an inverse operation of the derivative and so on, and jump from integration to differentiation without adding anything else. And we have Oskar Perron, this German mathematician. These two guys were able to define, so the Danjois integral and the Perron integral, and it turns out that they coincide. So the integral was called Danjois-Perron integral. And with this new integral, now we recover the primitive and can look at it and can look at the fundamental theorem of calculus with this new integral without any additional hypothesis. So in the late 30s, this theory was kind of complete. We had Lebesgue measure generated by the integral, and it's really important that a good integral generates a measure. So the Lebesgue integral generates a measure, and this integral generates the Lebesgue measure. We have integration of parts, invariance by Cauchy extensions, meaning that if you try to construct improper integrals, you're not enlarging the set of integrable functions, but you're keeping it. You don't get a bigger set. And monotone conversion theorem. So, for those who know Lemma ones from differential equations, and also topological methods, he said in his paper, Klimanesque versus Komanesque, trying to give a romantic description of integration theory. It looked like a little more, it took like a little more than 100 years after Liebman's dissertation, and some 40 years after Danjois and Perron works, to discover a simple human type definition of the Danjois-Perron integral. This new definition keeps the classic human sums, but modifies the limiting process. So we have the idea coming from the mind of these two brilliant mathematicians, Henstock and Henstock-Kurzweil. They gave independently a very nice definition of the Danjois-Perron integral, powerful as the Danjois-Perron integral, but so easy that you can teach first year calculus with this integral, with this definition. And this was done by Marcia Federson here in the US, and also by Jean Moulin himself in Belgium, he was doing this, trying to explain calculus 1 for freshmen, because then, especially for engineering students, you would have good convergent theorems. So we have here two definitions. In the first dot, we have the human definition. In the second dot, we have the Kurzweil definition. And I tried to write exactly the same thing, but we have the red thing different. So here we have a number, and here we have a function. And this way of partitioning the domain is the brilliant idea. So instead of dividing the domain into equal steps, this function here, can look at the integrand and see if it's behaving bad or not. If it's behaving bad, it divides into smaller pieces. So we have here, I'm not going to do this. We have here the partition of the interval AB with the TIs.
If that was the constant function, it would be a reminder.
Yes, perfect. So it's clearly in it. And we have these S's here that we say these are tags of the intervals. So somehow, and this is our construction when we are thinking of the area under the curve, we are thinking of rectangles, and then we are getting sub-intervals, and then thinking of a height here, so that we can think of f in this calculated here, and then we have the height of the rectangle. That's it. Okay. So Jean-Moulin continued the point. Instead of always allowing in the definition divisions with constant steps, which indeed forces the Riemann interval functions to be bounded and not to discontinuous. And this is the problem in comparison with Lebesgue integration. Kurzweil-Henstock's definition may force the step to be smaller around points where the function is discontinuous or tends to infinity. This idea of variable step introduced in abstract integration theory was already mentioned in this context by Euler. This is awesome. Well, this is why we have to continue looking at the originals, because we read, but not freely. And then after 10 years, we read it again, and then we get some pearls. And indeed, Euler said the following: we already have noticed that the intervals aj minus 1, that x is assumed to go through, must be taken very small, in such a way that the corresponding values f of aj minus 1 and f of aj do not differ too much one from the other. From this, one must decide if the intervals a1 minus a2 minus a1, etc., must be taken equal or unequal. Indeed, where the value of f of x does not change too much when x varies, an interval in which x moves can be taken without large without danger. On the other hand, in places where small changes of x lead to violent variations of f of x, one will have to take in the interval very small. So the idea of what we call a gauge or a caliber, this is going to calibrate the domain, is old. And sometimes it takes some time to manage to find it. Okay. So yes. So it's so funny because they could have discovered it much earlier. They could have, because it was here. And the Kurzweil integral is therefore known to deal well with highly oscillating functions. Because when you have highly oscillating functions, then you have to divide in smaller pieces because you have to take care of the behavior of the function that you have to take into account. So the purple one, which is the derivative of the green one, is an example of a function which is not very integrable, but it's good for Henstock integrable. Because Lebesgue clearly does not handle unbounded variation. And when I explain this to students, of course, think of a function around the x axis, and when you consider the normal bit, so you have everything like this, and the sum of these areas may not be convergent. So if this is so much, then it explodes. So this is why this other type of integration is called non-absolute integration, because we're not going to think of the integral of its absolute value, of the normal function or anything, because you cannot do it. You have to preserve the freedom to oscillate. Okay, this is another example, but you could talk to me and say something like this, like Marcia. These two examples you're giving us are examples of functions which are human improper integral. And indeed, they are. So why do you need this extra integral if you can do the limit and manage somehow to calculate the value of it? Okay. Let's continue. This is very nice. And with this definition, I can throw away measure theory when I'm teaching linear integration. It's just a way to work. Okay, so let's see. If you change this little bit in the Kurzweil integral, that is, you don't say that SI are in the intervals. But anyway, these have to be fulfilled like here. But like you can have this. You can have the mark outside, but still you need to have the interval inside the caliber. But you're not asking that the mark is inside. Yes. This very like stupid change gives us precisely the Lebesgue. So I don't need to go through measure, of course, we need measure theory because of many other things, but I'm just playing with you. You can throw away measure theory and define the vector integration by human sums, which is easy in the head of young people. And then immediately, because the sums are finite, you can separate into two parts and easily prove that the integral is linear. With Lebesgue integration, you have to prove peculiarity and so on 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 and so on. Then you have that the Lebesgue integral is linear. So it's really amazing. For monospace valued functions, the matching integral contains properly the Faulkner integral, just to happen. So the main feature is of the Kurzweil-Henstock integral is then to manage highly oscillating functions, and we know from physics that small particles are not to be described by oscillating functions, which are known as the wave functions. So we come again to this famous experiment, which transformed physics and made the mind of physicists like maniacs, trying to understand what was going on when little particles like electrons and photons were going through the two slits. Because contrary to their prediction, they would behave like waves. So this was going the so-called wave particle behavior for small particles. So when you go through one slit, you have probability P1. When you go to the second slit, you have probability P2. When you go through both slits at the same time, you're not having the probabilities. So this is the problem. So you are having here what is called some interaction or superposition. Okay, so we are now with these three guys, Schrödinger, Dirac, and Feynman. And we know about the Schrödinger equation, which says that the Hamiltonian, which is this part here, with involving the potential energy and the kinetic energy equals the total energy. And the solution to this equation is called a wave function. Okay, and because of the probabilities to reach the barrier here, the screen, then we have involved in this experiment this function of probability. Where is the probability that the particle is going to reach such a region? And okay, so the Schrödinger equation involves oscillating functions which are non-absolute convergent. And indeed, Feynman was thinking of these things in his PhD thesis. He came with his brilliant work, and he said once, where did we get that from? Nowhere. It's not possible to derive it from anything, you know. It came out of the mind of Schrödinger, invented in his struggle to find an understanding of the experimental observations of the real world. And indeed, it was a very educated guess to say that the Hamiltonian equals the energy, the total energy. And so they were like conjecturing it without exactly proving it. So Paul Dirac postulated he didn't prove that each path contributes with some probability amplitude with value. So this here is going to give the probability amplitude, and the square of the absolute value of the probability amplitude gives the density probability, which is the probability through one slit. And of course, this S here, as we know, is the non-minimal action, which was one of the nicest things that took the attention of Feynman when he was in high school, and he was like doing nothing in the classroom, and his professor of physics were, okay, I'll give you something to think about, minimal action. And then he started, like maniac, thinking of it all the time. So he proposes and that the contribution or the integral here of all contributions of possible paths would serve as a solution of the Schrödinger equation. He would not prove it. Again, it's a conjecture. Okay, so you have point A, point B. The particle is going from point A to point B. So these are fixed points. But the probability that the particle has to go from here to here, well, it can come to here, it can come to here, many possible paths. So now we are going to think of an integral over an infinite dimensional space. So the thing is the following. We have the E for finite dimensional spaces, say the integral of F over an interval AB, this AB being a compact integral of R. But now we are thinking, say, of the functions, continuous functions from AB to R. And you want to integrate an F over this C. So here it's okay. We take this AB and start doing this, okay? But now, what am I going to do with this? How am I going to partition such a space? Because this is what I have to do. I have to partition this. This is the first thing. Then I have to shrink it. And then I have the partition. And then I have to pass the limit. So, Feynman then discovered that a Schrödinger equation should be solved by a kind of averaging over trajectories. So this is why he came with the idea of this integral, known as Feynman integral. But as I told you before, a good integral has to generate a measure in the mathematical sense of a measure. But the Feynman integral doesn't. So they say that the Feynman measure is not a measure in the mathematical sense. The Wiener integral generates the Wiener measure. It's a good integral. The Lebesgue integral generates the Lebesgue measure. The Kurzweil integral generates the Lebesgue measure, but the Feynman integral doesn't generate any measure. So it's something that's not good in physics. So what was Feynman's idea? Let's put other slits, other barriers, let's think of the possible paths of a particle. So this was his idea. There are very interesting mathematical problems. So in the attempts to avoid the subdivision and limiting process, some sort of complex measure is being associated with the space of function x finite results can be obtained under unexpected circumstances because the measure is not positive anywhere, but the contributions from most of the paths largely cancel out. Thus, a non-absolute method of integration is required in order to allow the cancellation effects to survive. Otherwise, if you think an absolute integral, they disappear. This cancellation effect disappear because you sum one thing and the other thing, and this doesn't cancel. So the cancellation effect is when you have the intersection of one wave with the other. So you see this experimentally. Your integral, whether it's good or not, but trying to be a good integral, it has to manage this and keep it. So this is the cancellation effect mentioned by Feynman. So what is the Feynman integral? It's like a magic constant plus the integral, and the integral here, has that postulation right there with the minimum action inside it. And now this you can check the boxes are called at least the numbers and what is in each box of Feynman's from Feynman's office. And this is in the 26th box. This Patrick Montgomery was a student, a PhD student of Rockness. And he was trying to manage to define the answer over function spaces. And he wrote to Feynman, and Feynman wrote him back. I didn't know how to define the measure of the space of fact that was independent of the nature of what I was integrating. So I had to divide the interval of T into steps of size epsilon. And we find the measure as the product over all epsilon, where A is something magic coming from the wave equation and so on. And Feynman continues, only if A has this form will the limit as epsilon going to 0 exist. This is all necessary because facts which are not differentiable are the important facts. Of course, because we are with highly oscillating functions. Running motions are like this. So, okay, so he managed to give a constant with this, which is a magic constant coming from this A here. And in the attempt to solve Schrödinger's equation, we have this Fresnel integral. I'm going to show you. Thus, one needs to construct a measure in an infinite dimensional space, which is the space of all possible paths of particles. For instance, C of A B to R. And this construction involves Fresnel integrals because what you are taking into account are the cancellation effect that you cannot make it disappear. Since the Fresnel integral is not absolutely integrable, the final measure assumes negative and positive values, and the sigma additivity property fails. So, for instance, we have here this minus I here and square. If you put a norm in it, it disappears. You have a 1, and then the cancellation effect, this is going to explode. Because the absolute value is going to explode. because it's non-absolute integral. So the Henstock integration offers a different way to treat these Fresnel integrals. And so the thing is, now I want you to pay attention to the things I'm going to show you, not to read the whole thing, but let's think of a function h of an interval j and a point tau. This tau may be in j or not. Usually we put it in j, and we can write it as a function of the point and as a measure of the interval. Okay? So the usual Kurzweil-Henstock integral says that we can have a limit for the sum here, provided we have the caliber and so on. Okay, it's like we did in the. But we can think of integration over this space here. We don't need to restrict ourselves to continuous functions, but we can think of the space of all functions from B to R. And we are going to partition this space. So the idea is so linked to physics. That is so nice. And it's this one. First, let's think that we have two windows and the particle has to go through the two windows. We can go to here and add another window. So now the shrinking process has another window. So you are enlarging the dimension, or you can do as we do with Riemann integral. You can diminish the size of the windows and shrink it. The idea is to do the two things at the same time. This is the caliber in infinite dimensional spaces. You enlarge the dimension and shrink the intervals. This whole thing is the shrinking of the partition. And then you pass through the limits, and then you have the limits. And this is so connected with particles going through the spaces. So nice to think of it. So we can have, for instance, a function of this tau here, and tau is a continuous function. So a function of this variable, and the variable is a continuous function. And you can think of these, what we call cylindrical intervals. We could ask if this function here is integrable over this space. Okay, so Maldonado proved that every distribution function is integral. In particular, the Fresnel integrand is Henstock integrable, and the integral gives 1x as expected. Okay, so when we consider the Henstock integral to obtain a Feynman-Katz formula, which is the solution to the Schrödinger equation, meaning that we have a description of the wave function with this integral instead of the other one. We have the opportunity to manage the potentials and the energies, like they can have jumps and delays and be highly oscillating, and yet we have the solution. So I had once a student who now is my colleague at the department, And we studied the Schrödinger equation with undergoing jumps. And then later, we studied also the Black-Scholes equation, which is a modification of the Schrödinger equation. And also we have a Finkel's formula for that undergoing jumps. For instance, here, where we have a Brownian motion. And then we define the wave function as the integral of f, and f is given like this, and this v here can be like crazy potential, and this mu here generates a measure. So we have a function of a point in this cylindrical interval. This point is a function. And yet we can get the formula, and it's so in differential equations we can use many fixed point theorems to prove the existence of the. But here's such a stupid thing. But these simple things are sometimes so nice. This was such an educated guess that if you put this wave function in the formula, the Schrödinger equation is satisfied, then it is a solution. So the proof that this educated guess was a solution was simply by substituting it in the equation and see that it satisfies, so this is a solution. Without proving, without using many theorems from coming from little calculus or these kind of things. So with this background in non-absolute integration, and knowing that Kurzweil was defining the so-called generalized ODE, which now you can see in this math subject classification of 2020. It's now there in the number 34. It's some number there. So now we have these generalized ODEs as being a classification. It's very nice. And it encompasses all other of these differential equations. And then as the pandemic started in 2020, I gathered all my PhD students, and our university was okay doing online classes. So me and my colleague Federson were the only ones who were really working. All other universities, all other ex-students of mine, they were from federal universities and they were not online, they were not doing what to do with the students and so on. It took some time for the universities in Brazil to get updated, so they were doing nothing. And we were able to manage to write the book in 8 months. So as we finished the book in, say, 28 hands, 14 of us, I was thinking there must be a way to do the same thing for stochastics. And we got it. And the paper was published in the end of 23. We managed to get the definition of such an integral that contains what is called the Henstock, which contains the which is parallel to the Lebesgue integral for stochastic processes. And now our job is, okay, if I put delay, it is there. If I put time steps, it is there. Jumps, it's clearly there. Measure, it's clearly there, and so on and so on. And so we're going to give another huge class of differential equations for the stochastic processes and put everything inside. So for this, I come with physics, and because I talk so much about physics, this is just because of Philip. Because at some point we started to discuss things. He came from physics and then mathematics, and we started to discuss. So everything I've learned, I was advised by him. And okay, in 1905, we had the unbounded, where we have 4 papers from Einstein, and this is a picture of him in 1905. You have a paper on special relativity, a paper on photoelectric effect, a paper on mass energy equivalence, and a paper on Brownian motion. So Brownian motion is important in physics, you know that. Okay, I'm going to give you here, present you here, the Fokker-Coulomb equation, but I'm not from PDEs, so I'm going to think of it like a stochastic differential equation, where I have here a Brownian motion or a linear process. And now, the people descending academically from Henstock in Singapore, they define this Henstock integral, which carries the idea of Henstock to the integral, and so contains the integral, which is the analogous of the Lebesgue for stochastic process. And what happens is, this is very simple. We see here that the summands here look like Stilter style parts. The only difference is that you put the expectation outside because you're dealing with probability. But that's it. Okay, so we have integrability implying Henstock. And so in this paper I mentioned to you, we define what would be the Kurzweil related integral. It's related because the mark is on the left side of the integral. And again, we have here the summand, a mark, and an interval, which is expected, a sum, but because we are dealing with stochastic processes, we have the expectation. But that's it. That's it. That's simple. If you think that you are approximating by Riemann sums, but okay, we have random processes, when random variables and stochastic processes, so we have to talk, of course. The rest is the same. The way of thinking is the same. So, in particular, we can take a function of an interval and a mark and write it as a difference of a function of just any points, I would say. In this way, we come with the idea of Henstock-Kurzweil for the generalized ODEs, and we were able to manage what we are calling generalized stochastic equations. In particular, then, when we have this B Brownian motion and F some stochastic process, then we have the classic eTORs or Henstock or whatever. And as in all differential equations, the first expected result is to prove local existence and uniqueness of solution. And this was it. Thank you very much.